Journey to the future of the solar system and the destruction of the sun. In the coming billions of years, our sun will undergo a series of transformations destined to completely change the characteristics of every body in the solar system. The star that peacefully illuminates Earth today will first become a planet-devouring red giant, then a small white dwarf that will cool for hundreds of billions of years. The evolution of a star represents one of the most complex physical processes in the universe, governed by delicate balances between nuclear fusion, gravitational pressure, mass loss, and magnetic interactions. Every planet, moon, and minor body will experience dramatic changes, not only in surface conditions but also in orbital dynamics, atmospheric composition, and fundamental physical characteristics. This cosmic chronicle, based on the most recent computational models of stellar evolution and observations of planetary systems in various evolutionary phases, reveals a destiny as complex as it is inevitable for every world in our system. This spectacular journey will take you from today to the end of time, and after watching it, you too will never be the same again. The Sun today, a nuclear reactor slowly transforming itself. If we could peek into the heart of our Sun right now, we'd witness an incredible spectacle. The stellar core is operating like a gigantic nuclear reactor at 15.7 million Kelvin or 28 million degrees Fahrenheit, with a density of 150 grams per cubic centimeter, 150 times that of water, converting 4.3 million tons of matter into energy every second through the proton-proton reaction. It's a cosmic furnace that burns hydrogen, transforming it into helium and releasing energy so immense that it reaches us after an 8-minute journey through space. What might seem like a stable process actually hides gradual yet inexorable changes. Every passing year, our Sun loses 140 billion tons of mass through radiation and solar wind. That might sound like a lot, but for a star, it's like losing a grain of sand. However, this seemingly insignificant process has a curious effect. It causes all planets to gradually move away from the Sun, with their orbits expanding by about 1.5 centimeters per year. Imagine, while you're reading this article, Earth is slowly moving away from the Sun. It's the conservation of angular momentum that ensures this phenomenon. As the Sun loses mass, all planets gradually move away, with their orbits expanding proportionally to the stellar mass loss. 1.5 billion years, the beginning of the end. Let's now take a leap into the future of 1 to 2 billion years. Our descendants, assuming they still exist, will face a climate problem of unimaginable proportions. The Sun's brightness will increase by 15 to 20%. That might not sound like much, but the consequences will be devastating. Earth's average temperature will rise from 59 degrees Fahrenheit to 95 to 104 degrees Fahrenheit, 15 to 40 degrees Celsius, exceeding the critical threshold for runaway greenhouse effect. Water vapor is a powerful greenhouse gas, so the more water evaporates, the more Earth heats up, the more water evaporates. It's a self-feeding process that will bring about the end of Earth as we know it. Meanwhile, our planetary neighbors will experience equally dramatic transformations. Mercury, already the hottest planet in the solar system, will experience extreme heating. The dayside temperature will rise from 800 degrees Fahrenheit to over 932 degrees Fahrenheit, 427 degrees to 500 degrees Celsius, while the night side remains frozen at minus 279 degrees Fahrenheit or minus 173 degrees Celsius. Those small water ice deposits hidden in permanently shadowed polar craters will begin accelerated sublimation, forever eliminating the vast reserves of volatile materials on the innermost planet. Venus, which already lives in runaway greenhouse conditions with a surface temperature of 864 degrees Fahrenheit or 462 degrees Celsius, will become even more hellish. Its dense CO2 atmosphere will become even more turbulent, with surface winds increasing from 2.2 miles per hour to over 11 miles per hour, or 1 to 5 meters per second. That might not sound like much, but imagine 11 mile per hour winds in such a dense atmosphere. But there's interesting news. Mars will enter a temporary climate renaissance phase. The red planet, cold and desolate today, will see its average temperature rise from minus 81 degrees Fahrenheit to minus 49 degrees Fahrenheit, or minus 63 to minus 45 degrees Celsius. This will trigger partial sublimation of the polar caps, and water vapor content in the Martian atmosphere will increase, creating clouds and possible precipitation in equatorial regions. For the first time in billions of years, it might rain on Mars. 2.5 billion years. Farewell to Earth's oceans. Moving forward in our time journey to 2.5 billion years in the future, the Sun will have reached 1.3 times its current brightness, and Earth will experience catastrophic greenhouse conditions with surface temperatures of 140 to 176 degrees Fahrenheit, or 60 to 80 degrees Celsius. The oceans that once covered 71% of Earth's surface will be in accelerated evaporation phase. What happens next is a process of terrible beauty. Water vapor will reach the stratosphere, where, under the action of UV radiation intensified by the hotter sun, dissociates into hydrogen and oxygen. Hydrogen, being extremely light, will begin escaping to space at a dizzying rate. In just 500 million years, Earth will lose the equivalent of an entire ocean. The released oxygen instead will react with surface rocks, forming oxides and causing global reddening of the terrestrial landscape. Earth, once blue, will become a red planet. Meanwhile, Mars, now with an average temperature of minus 31 degrees Fahrenheit or minus 35 degrees Celsius, will experience more positive moments. The planet will experience partial permafrost thawing and formation of temporary lakes and equatorial depressions. Imagine, after billions of years of aridity, Mars will have liquid water on its surface again. 3.5 billion years. Mars becomes home. Here we arrive at one of the most fascinating chapters of this cosmic chronicle. Between 3 and 4 billion years from now, when the Sun reaches 1.4 to 1.6 times current brightness, Mars will enter its first temperate climate phase with average temperatures of 59 degrees Fahrenheit or 15 degrees Celsius at mid-latitudes, and up to 86 degrees Fahrenheit or 30 degrees Celsius in equatorial regions during summer. Think about it. Mars will become warmer than many European cities in winter. The Martian polar caps will retreat significantly, releasing enormous amounts of CO2 trapped in ice and thickening the atmosphere to 15 to 20 millibars, double current pressure. This would represent the optimal time for human migration to Mars, assuming our species is still around. The Martian environment of that period, while still requiring pressurized life support, would be incredibly more hospitable than current conditions. Tolerable temperatures for humans, water availability from melting permafrost, and a denser atmosphere that would greatly facilitate spacecraft landings and propellant production from atmospheric CO2. But beware, this Martian habitability window will have a limited duration of about 500 million years. That's a very long time by human standards, but a blink of an eye on cosmic scales. The absence of a global magnetic field will allow the solar wind, now intensified by a factor of 2 to 3, to progressively erode the thickened atmosphere. It's like having a boiling pot without a lid. The contents gradually evaporate. So anyone planning a long-term survival strategy should already think about the next destination. During the final centuries of Martian habitability, future humanity will need to prepare migration toward the outer solar system, with Titan as the primary destination and Triton as a long-term backup plan. 4.5 billion years. Inner planets become uninhabitable. Let's now move to an even more remote future. Between 4 and 5 billion years from now, Earth will have completely lost its oceans and most of its atmosphere. Surface temperatures steadily above 212 degrees Fahrenheit or 100 degrees Celsius will make survival of any life form we know impossible. Our home planet will have become a desolate and arid world. Mars will also begin its transition towards a desert world very different from what we know today. The atmosphere, continuously eroded by intensified solar wind, will gradually thin, but increasing solar brightness will maintain elevated temperatures. Average temperature will stabilize around 68 to 86 degrees Fahrenheit, or 20 to 30 degrees Celsius, transforming Mars into a hot desert similar to Earth's most arid regions today. No longer the cold, red planet we know, but a hot and arid world. However, while inner planets experience these climate dramas, outer planets will finally begin experiencing significant changes. Europa, Jupiter's icy moon, will go from minus 256 degrees Fahrenheit to minus 184 degrees Fahrenheit, minus 160 to minus 120 degrees Celsius, causing greater activity in the subsurface ocean hidden beneath its ice crust. It's the beginning of a story that will become very interesting for us in the subsequent billions of years. Hey guys, just a moment before we continue. Don't forget to subscribe to our channel, clicking on the notification bell, and leave us a thumbs up so you don't miss out on our daily videos. 5.4 billion years. The sun begins to die. We now arrive at the moment that will change everything. 5.4 billion years from now, nuclear fuel in the sun's heart will be completely exhausted. It's as if the cosmic furnace that has powered the solar system for over 10 billion years has run out of fuel. The core, now composed of pure helium, will begin contracting under its own gravitational weight. What happens next is a fascinating process. Nuclear temperature will skyrocket from 28 million degrees Fahrenheit to 90 million degrees Fahrenheit, 15.7 to 50 million Kelvin, while density increases by a factor of 10. The result? Solar brightness will rapidly increase from 1.65 to 3.5 times current levels in just 100 million years. Effects on planets will be dramatic and immediate, as if someone had suddenly cranked up the cosmic thermostat. Mercury will live its final moments. Daytime temperature will reach 1,472 degrees Fahrenheit or 800 degrees Celsius, causing vaporization of the last traces of volatile materials. The surface will begin a vitrification process, forming vast plains of molten silicates. Imagine a landscape of molten glass that solidifies and melts in a continuous cycle. Venus will become even more hellish. The already dense atmosphere will heat further, with surface temperature rising to 1,112 degrees Fahrenheit or 600 degrees Celsius. Surface winds will dramatically accelerate to 45 to 67 miles per hour or 20 to 30 meters per second. It's like a perpetual fire hurricane. Earth will enter its final phase as a habitable planet, becoming a sort of extreme Venus. Surface temperature will reach 302 to 392 degrees Fahrenheit or 150 to 200 degrees Celsius, while atmospheric remnants, now dominated by water vapor and CO2, will reach pressures of 5 to 10 bar or 5 to 10 times current Earth pressure. Surface rocks will begin thermal metamorphism processes on a global scale. It's as if the entire planet were put in a giant oven. Mars will experience one last dramatic climate convulsion. Equatorial temperature will temporarily reach 104 degrees Fahrenheit or 40 degrees Celsius, causing massive polar cap sublimation. It will be the last time Mars has a relatively thick atmosphere, albeit only for a few million years. 6.2 billion years. The Sun becomes an orange star. The Sun will officially enter what astronomers call the subgiant phase, characterized by rapid and dramatic changes. Its diameter will double while surface temperature decreases from 10,436 degrees Fahrenheit to 8,940 degrees Fahrenheit, or 5,780 to 5,200 Kelvin, giving the Sun a distinctly orange color. Brightness will exponentially increase from 3.5 to 8.5 times current solar levels. The solar wind will dramatically intensify, with particle density increased by a factor of 5 to 10. For the first time in solar system history, outer planets will begin experiencing significant climate changes. It's as if the solar system's habitable zone is expanding outward. Europa, Jupiter's icy moon, will see its first partial global thaw. Temperature will rise from minus 256 degrees Fahrenheit to minus 130 degrees Fahrenheit, or minus 160 to minus 90 degrees Celsius, causing active surface ice sublimation. But the most interesting thing will happen in its hidden ocean. The subsurface ocean will warm from 27 degrees Fahrenheit to 36 degrees Fahrenheit, -3 to +2 degrees Celsius, intensifying hydrothermal activity on the ocean floor. It's possible that life forms that evolved in that dark ocean will experience unprecedented prosperity. Io, Jupiter's volcanic moon, will become even more active. Total power dissipated by volcanoes will fuel sulfur plumes reaching heights of 500 kilometers, almost double current ones. Titan, Saturn's fascinating moon, will begin its transformation. Surface temperature will rise from -292 degrees Fahrenheit to -238 degrees Fahrenheit, or -180 to -150 degrees Celsius. Methane lake evaporation will accelerate, thickening the atmosphere. Even for Saturn's massive moon, this is the beginning of a story that will become very important for us in the next billion years. 7 billion years, the red giant era. Prepare for the most dramatic chapter of this cosmic chronicle. The Sun will begin its most spectacular transformation, rapidly expanding to become 15 to 30 times larger than today. Brightness will reach 150 to 300 times current levels, while surface temperature drops to 7,232 degrees Fahrenheit or 4,000 degrees Celsius, transforming our star from yellow to an intense red giant that would dominate the sky of any surviving world. But there's something even more interesting. For the first time since stellar evolution began, orbital changes will become significant. Solar mass loss, now accelerated to an incredible rate, will cause substantial orbital expansion. Mercury will move from 0.39 to 0.52 AU, or 36 to 48 million miles. Venus from 0.72 to 0.95 AU, or 67 to 88 million miles. Earth from 1.0 to 1.33 AU, 93 to 124 million miles. It's as if all the planets are being pushed farther from the Sun that's losing its gravitational grip. Mercury, farewell forever. Unfortunately for Mercury, this retreat won't be enough to save it. Mercury will be the first planet to experience total destruction. When the Sun reaches 50 solar radii, about 0.23 AU, its extended atmosphere will completely engulf the innermost planet. Temperature in that part of the solar atmosphere will reach 4,500 degrees Fahrenheit or 2,500 degrees Celsius, instantly vaporizing Mercury's surface. The destruction process will be both terrifying and spectacular. The rocky surface will transform first into lava, then into silicate vapor at 5,400 degrees Fahrenheit or 3,000 degrees Celsius. The heavier compounds of Mercury's core, iron and nickel, will resist longer, forming a tail of metallic vapors extending millions of kilometers behind what was once the planet's orbit. It'll be like seeing a gigantic comet made of vaporized metal. Venus, an uncertain but probably tragic fate. The fate of Venus remains one of the most debated and fascinating aspects of future solar evolution. When the Sun reaches 100 solar radii or 0.47 AU, Venus will find itself right at the edge of the extended solar atmosphere. According to scientists, the most likely scenario will be Venus gradually engulfed by the solar atmosphere. The dense Venusian atmosphere, which might initially protect it, will eventually cause atmospheric friction that gradually slows the planet, making it spiral inexorably toward the solar core. The death process would require 10 to 50 million years, during which Venus would transform into a giant comet with a spectacular tail of atmospheric vapors. Imagine an entire planet becoming a comet. Earth, suspended between life and death. Our home planet will find itself in the most precarious position of all. The most recent 2008 studies suggest Earth will probably be swallowed due to tidal interactions with the weakly bound stellar envelope of the red giant Sun. Earth's fate will depend on the precise balance between orbital expansion due to solar mass loss and friction caused by the extended stellar atmosphere. If Earth miraculously survives, it would emerge as a completely unrecognizable world. Completely remelted surface, vaporized atmosphere, oceans evaporated billions of years ago. The new Earth would be a sphere of vitrified rock with diameter reduced by 5 to 10% due to loss of volatile materials. No longer the blue planet we know, but a sphere of cosmic glass. Mars, the incredible rebirth of the red planet. But here's the most extraordinary surprise of this entire chronicle. Mars will enter its phase of maximum climate habitability. Initially positioned at 1.8 AU from the red giant sun, orbit expanded by 15% solar mass loss, the planet will receive about 45 to 50 times more energy than Earth receives today, bringing average surface temperature to 104 degrees Fahrenheit or 40 degrees Celsius, with summer equatorial peaks of 140 degrees Fahrenheit or 60 degrees Celsius, and summer polar temperatures of 77 degrees Fahrenheit or 25 degrees Celsius. Martian permafrost will completely melt in a few million years. Released water, estimated at about 100 million billion tons, will temporarily form global oceans 50 to 200 meters deep. The atmosphere will dramatically thicken to 500 to 1,000 millibars due to polar cap sublimation and CO2 release from soil, creating a greenhouse effect that will stabilize the climate. This will truly be the golden age of Mars. Subtropical temperatures, liquid oceans, an atmosphere dense enough to protect from radiation, and abundant water availability. For 200 to 300 million years, Mars will probably be more habitable than primordial Earth ever was. It'll be the perfect time for our extremely distant descendants to permanently relocate to the red planet. 7.3 billion years, the Sun at maximum expansion. The Sun will reach its maximum size as a red giant, 200 to 256 solar radii, with brightness 2,000 to 3,000 times current levels, and surface temperature around 5,940 degrees Fahrenheit or 3,300 degrees Celsius. To give an idea of the dimensions, the expanding solar globe would exceed even Earth's orbit. Outer planets. Europa becomes a new ocean world. Europa will experience its most spectacular transformation. Europa's subsurface ocean, finally freed from its 20-kilometer thick ice crust, will emerge as an exposed global ocean 60 to 100 kilometers deep. Ocean temperature will reach 59 degrees Fahrenheit or 15 degrees Celsius, perfect for complex life forms that might have evolved in darkness for billions of years. Hydrothermal activity on the ocean floor will intensify by a factor of 10 to 20, creating an energetically rich ecosystem that could support a surprisingly complex biosphere. It'll be as if Europa transforms from an ice ball into a true ocean world, with waves, storms, and perhaps even marine life that can finally see sunlight for the first time in solar system history. But the real protagonist of this era will be Titan, which will become humanity's final destination during the Sun's red giant phase. Titan's transformation will be absolutely spectacular. Surface temperature will rise from minus 290 degrees Fahrenheit to 32 degrees Fahrenheit, or minus 179 to 0 degrees Celsius, causing complete evaporation of methane and ethane lakes that characterize its landscape today. The nitrogen atmosphere will thicken, creating a greenhouse effect that brings surface temperature to 68 degrees Fahrenheit or 20 degrees Celsius. Surface water ice will begin melting, forming the first liquid water oceans in Titan's history. This phase will represent Titan's moment of maximum habitability, optimal surface temperature for humans, a dense atmosphere that will protect from cosmic radiation, liquid water availability, and rich organic chemistry developed over previous billions of years. 7.6 billion years, the most violent phase. After 600 million years as a red giant, the Sun will experience the most violent moment of its entire existence. The solar core will reach critical density of 1 million grams per cubic centimeter and the incredible temperature of 180 million degrees Fahrenheit or 100 million degrees Celsius. At this point, something extraordinary will happen. Degenerate helium will explosively ignite through the triple alpha process, a nuclear reaction that converts 3 helium-4 nuclei into carbon-12. Released energy will equal 100 billion joules, an amount of energy equal to 100 billion times current solar brightness concentrated in a few terrifying minutes. It's as if the sun suddenly became a star-sized nuclear bomb. Fortunately for surviving planets, this energy remains trapped within the massive stellar envelope and isn't directly observed from outside. The cosmic nuclear winter. What happens next is equally dramatic. The sun will rapidly contract from 200 to 10 solar radii in less than a million years, assuming a yellow-orange color. Surviving planets will experience brutal and sudden cooling. Solar brightness will collapse from 2,000 to just 50 times current levels, causing a cosmic nuclear winter lasting 10 million years. It's as if someone suddenly drastically lowered the thermostat of the entire solar system. Mars will rapidly return to hot desert conditions, with temporary oceans refreezing in a few centuries, though temperatures will remain higher than current ones. Europa will see its exposed ocean freeze again, reforming an ice crust 30 to 40 kilometers thick in just 100,000 years. Titan will return to its original atmosphere, with methane recondensing to form the surface lakes that characterize the satellite in remote epochs. At this point, Triton will represent our last habitable frontier. This large moon of Neptune, with its 2,706-kilometer diameter, will be in the optimal habitable zone during the final phases of the red giant. Humanity's strategic migration will follow this fascinating sequence: Earth to Mars, Mars to Titan, Titan to Triton, accompanying the expansion of the solar habitable zone over at least a billion years. 8 billion years, the second red giant phase. After 130 million years of relative stability, the Sun will experience its final spectacular transformation. Core helium will be completely exhausted, leaving a carbon-oxygen core surrounded by concentric fusion shells. It's like a cosmic onion with different nuclear reaction layers burning at different temperatures and rates. The Sun will enter what astronomers call the asymptotic giant branch, a phase characterized by dramatic thermal pulses every 1,000 to 10,000 years, causing incredible brightness variations between 1,000 and 5,000 times current solar levels. Imagine living on a planet where every 10,000 years or so, the Sun suddenly becomes 1,000 times brighter for several centuries. During this final phase, the Sun will lose mass at an impressive rate of 100,000 billion tons per year, carrying away 30 to 40% of its original mass in just 20 to 30 million years. It's as if the star is literally evaporating into space, blowing itself away with an increasingly intense stellar wind. 8 billion years, the Planetary Nebula. The final phase of the giant will culminate in a series of catastrophic expulsions, during which the Sun will completely eject its outer layers in 4 to 6 explosive events, each separated by about 100,000 years. It's as if the star is literally stripping off its cosmic clothes, layer by layer. The final stellar wind will reach speeds of 1,243 miles per hour, sweeping away the last remnants of the solar atmosphere and finally revealing the incandescent stellar core, a white protostar with surface temperature of 360,032 degrees Fahrenheit or 200,000 degrees Celsius. The resulting planetary nebula will extend 2 to 3 light years, illuminated like cosmic neon by ultraviolet radiation from the central core. Expelled gases rich in carbon, nitrogen, and oxygen created during previous phases will form complex structures of indescribable beauty. Multicolored concentric rings, brilliant density nodes, and polar jets extending trillions of kilometers. It'll be like a giant cosmic firework lasting tens of thousands of years. The few planets surviving this final phase will experience ultraviolet radiation bombardment 1,000 times greater than current levels. Any residual planetary atmospheres will be ionized and dispersed into space, while rocky surfaces undergo deep chemical alterations. Mars, now positioned 3.1 AU or 288 million miles from the stellar core, will receive UV flux that definitively sterilizes any residual biological traces, transforming the surface into a desert of vitrified regolith that will glow under ultraviolet light from the dying sun. When the spectacular planetary nebula dissolves after 50,000 years, only the exposed stellar core will remain, a white dwarf with 0.6 times the original sun's mass, but compressed into Earth-sized volume. Density will be 1 ton per cubic centimeter, so extreme that a simple teaspoon of this material would weigh as much as a car. Its matter in such an exotic state it defies our imagination. During this period, planetary orbits will finally stabilize at their definitive positions. Mars at 3.1 AU or 288 million miles, Jupiter at 9.5 AU, Saturn at 17 AU. Surface temperatures will stabilize at their final, incredibly cold values. Mars minus 328 degrees Fahrenheit or minus 200 degrees Celsius, similar to Pluto today. Jupiter minus 382 degrees Fahrenheit or minus 230 degrees Celsius. Saturn minus 400 degrees Fahrenheit or minus 240 degrees Celsius. Uranus and Neptune minus 418 degrees Fahrenheit or minus 250 degrees Celsius. The long cosmic sleep. After billions more years of gradual cooling, the white dwarf will have cooled to 10,832 degrees Fahrenheit or 6,000 degrees Celsius, similar to current sun surface temperature but with reddish color due to its reduced size. Brightness will have dropped to 1/10,000th of today's sun, making the star practically invisible even from distances of a few light years. The solar system will be immersed in profound and definitive cosmic silence. Surviving planets will orbit in complete darkness, illuminated only by the white dwarf's faint reddish light that will seem little more than a very bright star in the night sky. There will be no more auroras, no more seasons, no more life as we know it, only silent movement of dead worlds through frigid space. Surviving planets will share similar and extraordinary fates. While their orbits gradually decay through gravitational wave emission, taking 10 to the power 15 to 10 to the power of 18 years to slowly spiral toward the white dwarf, the very matter they're composed of might eventually completely dissolve into photon and neutrino radiation, leaving behind only pure energy dispersing in the expanding universe. 100 billion years, the black dwarf phase. When the white dwarf temperature reaches near absolute zero, then all outward radiation ceases, and what was once our sun will become a black dwarf, an extinguished ember the size of Earth, absolutely unobservable. Reaching this phase has never been observed in any star, since the process requires time longer than the universe's age. And here we're literally beyond any human comprehension capacity. What remains is the consolation of knowing that for us Earthlings, if we want and if we can, there will be the possibility of extending our survival for at least 1 billion years by migrating to increasingly outer planets and moons. We, obviously, won't be there.